This video. Here we are going to break down how windows work when it comes to heat. We'll separate the heat from conduction, that's the heat that moves through the glass itself, from the heat you get from the sun. I'll introduce you to two key terms, U-value and shading coefficient, and we'll compare different types of glass, like clear, low E, and reflective, to see how they perform in both summer and winter. Finally, you'll learn how to figure out when your window area becomes the biggest factor in your building's total gain. Now, before we get into the analysis, let's map out our journey. Here's a quick look of what we'll cover in the next few minutes. We'll start by breaking down the two main ways heat moves through your windows, conduction and solar gain. Then we'll dive into the U-value and the solar shading coefficient. These are the key numbers you need to understand. After that, we'll compare a few different glass types and then wrap up by showing you why a window size and area can have a huge impact in your total heat gain. Okay, let's look at what you'll be able to do once we are done with this video. By the end, you'll have the knowledge and skills to define and apply U-value and shading coefficient. Those are the two key numbers we'll be using. You'll also be able to perform a quick two-term calculation to figure out a window's heat gain. And finally, you'll have the autonomy to make smart climate-aware glazing recommendations. That's just a fancy word for the type of glass you should use. So get ready. We are about to make you a fenestration expert. Before we get into the analysis, let's start with a question to get you thinking. Imagine two identical rooms on a clear summer day at noon. One room has a large double-sized window with clear glass facing north. The other has a small window, only half the size of the first, but is facing west and has no shade. Which of these two rooms do you think will overheat more? It might seem like a simple question, but the answer isn't so obvious. Your first instinct might be to save the room with a bigger window, right? But after all, more glass means more heat. But what if the orientation, the time of the day, and the lack of shading are more important than the size of the window? These questions force us to think about the difference between heat that comes in because of a temperature difference, that's conduction, and that powerful energy we get directly from the sun, which we call solar gain. So what information will you need to actually solve this problem? Think about all the factors involved: the U-value of the glass, the temperature difference, the amount of solar energy hitting each window, and something called the shading coefficient. We'll touch on all of these concepts in this video, giving you the tools to not only answer these questions, but to make smart decisions for design choices in the future. First, we need to understand the two main ways heat gets through a window. The first is through conduction. That's the heat that moves through the material itself. It's happening all the time, day or night, as heat flows from a warmer space to a cooler one. We use the UA delta T term to describe this, where U is the U-value, a measure of how well the window receives heat flow. A is the window's area, and delta T is the temperature difference between inside and outside. This is a crucial distinction, improving your window's U-value by using things like low E coatings or special guides fills in the panes will reduce heat loss in the winter and heat gain in the summer, which it's a year-round win. The second pathway is all about the sun's energy, which we call solar gain. When sunlight hits the glass, some of it is reflected away, some of it is absorbed by the glass, and some is transmitted directly through it. The heat you feel inside comes from the transmitted light, plus some of that absorbed energy that radiates inward. We use a metric called the shading coefficient, or SC, to model this, which is basically a number that tells you how much solar heat a window lets through. Unlike conduction, solar gain is all about the sun. So it's a huge factor during the day, but basically zero at the night. This is why a west-facing window in the afternoon can make a room feel like an oven, even if the temperature outside isn't that high. It's absolutely essential to keep these two terms separate when you are calculating a building's total heat load. Why? Because the physics are different. The solutions are too. You improve conduction by making a window better insulator, things better frames and special glass. You control solar gain with things that block sun's energy, like coatings, tints, or external shades. Keeping them separate helps you to pinpoint the real problem and choose the right fix. Now let's zoom in on the U-value. Think of it as your window's insulation rating. The lower the U-value, the better the window is at resisting heat flow. It's a single number measuring watts per square per meter per Kelvin. Measuring watts per square meter per Kelvin. That represents the entire window system, from the glass panes and the gas between them to the frame itself. This allows us to treat a complex window as a single unit when we are calculating heat flow. We use the UA delta T term to calculate the total heat moving through the window due to a temperature difference. So how does this work? We model conduction using the formula Q of conduction equal to UA, and the temperature difference between the indoor ambient and the zone, the outdoor ambient air and the zone. This formula is a two-way street. In the winter, when it's colder outside, so when the outdoor air is low temperature, our outdoor air temperature is lower than the zone temperature, heat escapes from your home, resulting in a heating penalty. In the summer, when it's warmer outside, so when the temperature of the outdoor air is higher than the temperature of the zone, heat comes in, adding to your cooling load. Because this term is about the temperature difference, it's always working day or night. The good news is that you have control over this. By choosing a window with a low U value, you can reduce heat loss in the winter and heat gain in the summer. We can achieve this with things like special low E coatings on the glass, filling the space between the panes with an inner gas like argon, or using better insulated frames. When you are comparing different windows or reporting your results, always remember to keep the conduction term separate from the solar gain. This helps you figure out whether you'll get more bang from your buck by improving U value or by focusing on reducing solar gain. So we talk about conduction and the U value. Now let's focus on solar gain. This is all about the energy coming directly from the sun. We use something called the shading coefficient, or HC, to measure this. It's a simple ratio that compares how much solar heat a window lets into a standard 3mm thick clear pane of glass. This single number combines all the complex optical and thermal effects, making it a great shortcut for us. A lower SC means less heat from the sun is getting inside, which is why a window with a special coating might have a value well below 1. Other important coefficient is solar heat gain coefficient, SHGC. That is a fraction of incident solar radiation that is admitted through a window, both directly transmitted and absorbed, and subsequently released inward. SHGC is a more modern and widely used standard, especially in North America. It is a value between 0 and 8 and 1. A lower SHGC means less solar heat gain, which is good for climates with high cooling loads. Now the formula itself here. So this simple model tells us how much solar heat is coming through the glass. Here A is the window's area, F ref is the portion of the windows that is directly sunlight, SC is our shading coefficient, and GT is the intensity of the sun's radiation hitting the window. Remember, this term is entirely separated from the UA delta T conduction term we discussed earlier. This is also why things like a window's orientation are so important. A west-facing window at sunset is going to have a much higher GT than north-facing one. The good news is we have several ways to control solar gain. The most effective way is with external shading, like an overhang or a fin, which can dramatically reduce the amount of solar radiation hitting the window. You can also make smart choices about the building's orientation to minimize sun exposures on the hottest facades. And of course, you can select glazing with different spectral properties, things like tints, reflective films, and special low-E coatings. These help lower the SC without always blocking natural daylight. It's all about balancing the solar heat gain against your needs for the lighting and comfort. When choosing a window, your climate and the season should guide your decisions. For summer cooling, our main goal is to block as much solar heat as possible. In this season, the shading coefficient is your most important number because at the peak sun, the solar gain term is usually much larger than the conduction term. You'll want to prioritize glazing with a low SC, like a tinted reflective or a spectrally selective low E window. This is especially true for west-facing windows, which get hit with most intense afternoon sun. While the uvalue still matters, focusing on lowering the SC will give you the biggest bang for your buck in reducing your peak cooling load. For winter heating, the situation is reversed. Our priority shifts to keeping heat in. Here, the low U value is the most critical factor, as the large temperature difference between inside and outside makes conduction the dominant path for heat loss, especially at night. A low U value will significantly reduce your heating penalty. However, for a south-facing window in a cold climate, you might still want a moderate SC to allow for some beneficial passive solar gain during the day, which can help offset your heating needs. Whereas south facing if you are in a north hemisphere, but if you are in the south hemisphere, a north facing window. Now, for the third point, during the shoulder season, so this is spring and fall, the balance is all about comfort and daylighting. You'll need to manage solar gain and glare on clear afternoons while still letting in natural light. This is where dynamic shading like blinds or smart shades becomes invaluable. It allows you to block unwanted sun when you need to and open for daylight when you don't, giving you total control without having to change with a window itself. Your final recommendation should always consider whether you are trying to optimize for energy, peak load, or just plain comfort. Now let's compare windows to the rest of the building exterior, the opaque surfaces like insulated walls and roofs. The U value of a typical wall is much lower than a window's U value, and the wall doesn't have a solar gain term from direct sunlight. This means a wall's heat gain per square meter is usually much smaller than a window's. A window, however, is a different story. It has a higher U value and during the day a significant solar gain term. When you add these two together, a sunlit window can have a much higher heat gain per square meter than the wall. This is why even a relatively small window can have a disproportionate impact on your building's total heat load. The total heat gain from the window is its intensity, watts per square meter, multiplied by its area. This brings us to a crucial design insight: window-to-wall ratio. Even a modest increase in the amount of glass can make windows the dominant factor in a building's peak heat gain, especially in summer. This is often the case on west-facing facades, where intense afternoon sun makes the window's heat gain far outweigh the heat coming through the much larger opaque wall. To make this clear, in your reports, always present both the heat gain per square meter and the total heat gain for each component. So let's quickly recap the most important takeaways from this video. The two-part model. First, remember the two-term model from window heat gain, the conduction term UA delta T and the solar term SCGTA. These two terms represent the completely different physical processes. Heat moving through a material due to a temperature difference versus heat coming directly from the sun. You must always keep them separate in your calculations to get an accurate result. Second, you know when to prioritize one term over the other. In summer, especially on sun-exposed facades, the solar term almost always dominates the peak heat gain. This means focusing on a lower SC or HGC or even shaving will have the biggest impact. In winter, the conduction term is usually the main driver because the temperature difference is so large, so your focus will be on a lower U value. Finally, never underestimate the power of a window size and orientation. And a small increase in your window to wall ratio or a particular orientation, like a west-facing window, can make the window a single large contributor to your building's peak heat gain. Even if the rest of the wall is well insulated. Always examine these factors to truly understand what's driving your building's energy performance. So in this video, we cover the basics, but there's so much more to learn about optimizing windows. Here are a few topics you should explore to become a true expert. First, dive deeper into the spectral selective low-E coatings. Unlike neutral low-E coatings that reduce both visible light and heat, these advanced coatings are specially engineered to block the sun's infrared heat while letting in most of the visible light. This allows for excellent daylighting while still providing a very low shading coefficient. They are a game changer on balancing light and heat in sunny climates. Next, study the effectiveness of external shading. Unlike coatings, external devices like overhangs or vertical fins block solar radiation before it even hits the glass. Their effectiveness is highly dependent on the window's orientation. For example, a simple overhang is incredibly effective on a south-facing or north-facing, depending on your hemisphere, window, while vertical fins are best for east or west-facing window. Finally, consider how all of this ties into the lighting and glare. A window isn't just about heat transfer, it's also about providing natural light and visual comfort. Very low SC might be great for reducing heat gain, but if it makes the room too dark or creates glare, it's not a good solution. The best facade design balances the thermal performance of a window with its visual impact, often using dynamic shading to manage this trade-off throughout the day. Well, thank you for watching this video. I wish to see you in the next one. Bye.